Coming up on this episode of the IoT Inc. Business Show.
The underlying model is a finite element model that also holds what we call state information about the dynamics of the structure, not only the situation now, but also the history that this model is having, physical states that this model can have. So in some sense, we're modeling both the thing itself in the Internet of Things and the behavior of nature, the context of the thing.
The reason the digital twin, or software-defined product as I prefer to call it, is the most important IoT tech is because it's the basis for the unique functionality possible by using the Internet of Things. Going beyond smarts and connectivity, it's this unique functionality that creates value, enough value that results in a profitable IoT product. In this episode of the IoT Business Show, the second in a series on the digital twin, I speak with Arnulf Hagen about the underlying models of the digital twin and the high-level ways you can use them to create value.
All this and more on this episode of the IoT Inc. Business Show. The people, the business, and the technology of the next generation internet. This is the IoT Inc. Business Show. And now, here's your host, Bruce Sinclair.
Hello and welcome to the IoT Inc. Business Show. This show is made possible by sales of my book, IoT Inc., published by McGraw-Hill, and the IoT Inc. Certified IoT Professional, or ICIP, online training and certification program. Become a certified IoT professional by completing the program's 3 courses: ICIP Technology, ICIP Business, and ICIP Strategy and Digital Transformation. Details of which can be found at www.iot-inc.com. That's www.iot-inc.com. With me today on the IoT Show is Arnulf Hagen. Arnulf is Managing Director of SAP-owned Fedem Technology, as well as Chief Product Owner in SAP. He's responsible for the development of physics-driven, high-fidelity digital twins. He has worked the last 15 years as both an entrepreneur and executive manager. Arnulf, welcome to the show.
Hi, Bruce. Thank you.
So
nice to be here.
Were you the founder of Fedem Technology?
No, I wasn't the founder of Fedem Technology. Fedem Technology is, it's a relatively old company. It started in the 90s but I've been now managing director for 4 years, and I was responsible for the transformation into an IoT company.
Now, what was the company doing before it was doing IoT?
Well, Fedem is it's what we call here in Norway has had a lived life. It has gone through different stages. It was founded as a spin-off from the university and the research community here in Trondheim, from the structural analysis environment, based on ideas about making finite element analysis programs, applications doing rapid simulations, such as would be needed in that case in those early days to facilitate the structural analysis of, for instance, cars and moving things.
So, I mean, finite element analysis has been around for a long time. So this was more like a living model or like a real-time model, or what was different about it?
Well, yes, you're absolutely right. Finite element analysis has been around for quite some time, probably about 50 years. But it's very numerically intense. It's finite element analysis is a number crunching maneuver. So that when you're doing an analysis, you're having to go through a lot of mostly unnecessary calculations to get through to the results you're actually interested in. So one of the main ideas behind behind the Fedem when it was established was to reduce these this problem of number crunching into a more mathematical problem, so that it could be something that took hours to resolve before in other programs would take seconds to resolve in Fedem.
Okay, so you simplified the mathematics, or you just use different mathematics to be able to do the calculations?
Yeah, simplified the representation of the physical object. So by using what's called super elements instead of normal finite element analysis.
Okay, well, I want to ask you about that, but I probably shouldn't. So let me ask you about IoT. Why the transition to IoT, and like who came up with the idea, and was it something that was pulled by customers, or was it just like a new idea?
Well, it's I have to backtrack a bit then, because just to go through the some of the history behind from the early start until now, because initially the model was therefore of a thing. I mean, it was used for virtual prototyping of things, moving things, Fedem. And
Sure.
with this efficient calculation, it was possible to create time domain simulations, right? So you do an analysis, tick time, and then a new analysis is done, tick time, and another one. So that this could be a car running over a sidewalk, or a satellite unfolding its solar panels, or a crane lifting an object, or a robot doing an operation, could be modeled in time. This was one of the basic ideas. The other was that a moving object is subjected to, of course, physical forces. So in addition to the finite element solver itself, was a physics solver that would represent Newton's physics, classical physics, so that all operations or all relations that could be or all forces that a moving object was exposed to would be calculated. This would make it possible to not only represent the static or the state of the object right now, but the development of that state throughout time. And thus we, in addition to implementing a virtual control system, so that this moving object didn't only passively behave according to the environment, but also could respond to the environment, or could even instruct the system to perform a particular task, like in a robot. This together made Fedem into a virtual prototyping tool, then used in a design stage for virtual prototyping of these objects that ultimately would come into physical existence. So it was a supplement or a substitute for physical prototyping, which was very important in in those days. It was a discussion. How could we use digital means to replace expensive physical prototyping of cars or robots or stuff like that?
So it was just a paraphrase. So it was a simulator in a sense, and a simulator specifically for the physics and the physical representation, or just the physics of the object that's on the object?
Well, it's both the physical representation and the physics of the object, the physical state of the object. So by this, we could monitor any kind of state property in the object that were related to the Newtonian physics, such as accelerations, velocities, g-forces, or stresses, strains, forces, bending moments, and stuff like that. So that's, So this was, you can imagine, this was a fast simulation tool in the 90s. And as we chugged along throughout the 2000s, Fedem started becoming an engineering company. And when I came in 2013, the software was mostly used internally to solve complex problems in the offshore sector or the wind sector. But throughout these years, the Moore's law of doubling the processing speed every 1.5 year, or what it ends up being, made the fast, very fast in 90s, super fast in the 2000s, and then you say ultra fast in this decade. And what we saw in 2013-14 was that, now we can do complex simulations in real time, where we earlier could do real simulations in almost real time. That was when the idea came that why don't we employ this to make real-time representations of complex moving objects in the physical world, making virtual models that then could be used for concurrent analysis, picking up signals from the real world, the physical world, and transforming them into digital representations.
Okay, so that's the bridge then, because, up to this point, you've been describing pretty much what you were doing before, but what you're layering in now and how you're making the connection to IoT was the data, the real-time data that's coming in. You could also layer that onto the model, so it's a living model, and not only is it a living model, but you can see how it's living in more or less real time. That was kind of the connection?
That was the connection, exactly. And how
was that made? Was it through one of your customers, or where did this idea, of bringing in the living model, I suppose, come from?
Well, I don't know how. It was a leap. I think we just we just needed to find out how to exploit the opportunities residing in this basic virtual prototyping tool. To see that opportunities that didn't before exist suddenly now existed. So it was in some sense a logical development, but it was also a leap. We had to do some major shifts in thought to make this work.
Yeah. No, I agree. And I think, we're going to get into this, and everyone, what we're going to be talking about are digital twins in particular. But I think, when you think about the models that we've had and the models that we're using in IoT, this is probably the big differentiator. Although we've had them, let's say, in video games for a long time, but having a living model that's bringing in live data is really, I think, the nuance. And maybe, Arnulf, you could add more detail, but I think that's really the nuance that's different from, let's say, an IoT model, and we'll relate that to the digital twin in a moment. But the IoT model and, say, the models that we've had in engineering and all the different types of models that we've been using probably for the last 50, 100, 200 years. Do you have any other, I guess, detail how you would think that it's maybe a little bit different than what we've been doing up to this point in time with modeling?
Yeah, well, I think you're onto the right track in your thinking there, because how we did this was also that, we're doing a virtual prototyping. This is a step before the physical prototyping. Before then, we just did design analysis. Now, what is the next step after a virtual prototype? Well, you instantiate a physical thing from it. But why do you stop kind of prototyping, even though you have a physical thing? In the virtual prototype, you test out whether your scenarios seem to be okay. So you implement this in the physical world, and then you say, okay, so now the car is driving, the crane is operating, the robot is doing its thing. But there is no reason why you should stop, as I say, having a digital representation of that thing. So then if you do have this virtual prototype, why not instantiate also this virtual prototype into, what we call now a digital twin. I'm not very fond of that word, but because it's overloaded now, it's starting to get worn out, even before it's introduced. But then we, after doing this, then we have a mirror, or we have a replica, a clone, or something that mimes the behavior in the physical world.
Right.
So that's yeah.
So well, let's talk about that a little bit more. So what we've been leading up to here has been the development of a real-time model that's taking in live data. And like you said, it makes sense, right? We used a virtual representation to simulate something. We did the simulations, then we just moved on to the physical. And what you're saying here is, yeah, we can do that, but we can also keep the digital because we might be able to do other things with it. So we'll talk about that, but let's get your definition. What is a digital twin for everyone listening now?
Oh, okay. This is we have this up in the discussions here internally, because when I say a digital twin, of course, I'm assuming that you have an image of it that is similar to my image of it, but then yours may differ from mine, and then you answer based on some other image than I have, and then we can spend all day talking about two different things, right? Yeah, so this is a general issue, general problem that I think we need to talk about the underlying, the where's the beef? I mean, where's the beef of the digital twin? Lift up, the Wendy's ad at some time. You had to lift up you had to unwrap the burger before you saw what it really was, but then you had to take up the bun and then in the end you came down to the beef.
A small little piece of beef, yeah.
Small little piece of beef. So I think we have digital twins ranging from the small and dry beefs to the really luscious, tasty beefs. And but if we go into this, the digital twin, in our view, is a virtual model that, to varying degrees, represent a physical situation. And what I'm talking about now, the remainder of this talk is mostly the what's called high fidelity digital twin, or physics driven digital twins, in which we assume that this virtual model should represent as much of the physical reality as possible, or as needed in the context. So this high fidelity digital twin, the high fidelity thing, the virtual model, is something that then takes up signals or gets measurements from the physical, and translates those or transfer those images, these signals, into a virtual model, and stimulates that virtual model, so that by looking at the virtual model, you get a picture, or you get an idea about how the physical world is. The smallest of these, of course, if you say that I'm saying everybody will have a digital twin now soon. In the easiest of cases, you can say that if I say just I have a thing, I have a refrigerator, or I have a door. I have a door. I get making digital twin of this door, and I have a sensor that says door open or door closed. It's a binary sensor saying either or, and I transfer this information to my door virtual model, and this door virtual model will have simply one state, open or closed. And then I have a digital twin, because I can I can then track the history of opening and closing of this door.
Right, so that's the most basic, you're saying, basically a Boolean digital twin.
That would be almost good. That's a good term, Boolean digital twin. It's a very, in my view, don't know these terms again, but a low fidelity digital twin, you don't have a very high resolution. You don't have very many states that you can monitor. You don't you cannot really do very much with it except knowing that the door is open and closed and maybe regulate something or send an alarm like that based on this. But then on the other side, let's take a case that we have implemented in wind turbine in the north of Norway. We pick up signals, and these signals are motion information. It's based on observing the behavior of the structure. These motion signals, as you would know in Newtonian physics, we can move from positions to velocities to accelerations if we just tick time. And by knowing the deformation of a structure, you also know the forces that are acting on that structure. So what we are doing is sending this positional information or the motion information into a true copy of this digital twin and back again to a finite element model, a reduced model, that at each time instance says, well, if the position on that particular point is sent into the model will instantaneously calculate the responses in the structure and wait for the next time tick, wait for the next sensor signal, and then do the same thing and deduce what kind of behavior has taken place between these two time ticks. So, since this is a finite element model, we can go into any point in the structure and find out what kind of stress did this particular situation cause in that particular position in the structure, or what G-forces are acting on the wind turbine, on the mechanism on top, or what bending moments are acting on the foundation, the footing of this wind turbine, or what other information we could extract based on the fact that we do have a quite rich model and a quite rich representation of the physics.
Okay. So let me just sort of understand this a little bit more. The Fedem model, so at the heart of a digital twin, is going to be this model, and I'm getting the sense that the model that you're using, since it's describing physics and in particular Newtonian physics and in particular structural Newtonian physics, then you're using the finite element model. Is that the underlying basis? Is that the underlying model for Fedem's digital twin?
Yes, the underlying model is a finite element model but the finite element model that also holds what we call state information about the dynamics of the structure, not only the situation now, but also the history that has that this model is having, and the physical states that this model can have. So in some sense, we're modeling both the thing itself in the Internet of Things and the nature and the behavior of nature, the context of the thing.
Okay. Now let's look up a little bit and answer the question why. So when we were doing the virtual prototyping, then it made a lot of sense for, let's say we had a digital twin of an automobile. We crashed it on a curb, or we crashed it against another automobile, and we could see how it reacted, and in particular, the damage and if anyone was hurt inside. So there was a purpose for that. Now in IoT, why is it important to have this digital twin? You've used the example of the wind turbine, and it's sounding very much an engineering focus. So is it for engineering purposes, or give our audience now a little bit more I guess, context or reason why a digital twin is important to do, why it's important to have a digital twin?
What we are doing, we're digitizing everything now, and if we're going back, if we're seeing what we're actually doing in the digital economy, in the end, we're hitting the physical economy, the analog, right? So traditionally, this physical, we're basing our digital analysis in the end of physical observations. At some point, these were punched in. Somebody went out there, observed a thing for maintenance purposes, or for to find out if something had gone wrong, and punched it into some place in a software, and the software did the analysis. This was sometimes this is costly. It delays. It was a time delay related to it, but in some cases it would be very dangerous to access a thing. Or it could even be impossible if it's subsea or if it's in the space. So what we started doing then was to instead of translating this by physical observations, by looking or measuring by human people, we put sensors on the things, and we joined this with communication technology to send sensor signals into the databases or into repositories where the analysis would be taking place, finding out if some action would be needed, or if some danger had occurred, or if some improvements could be made to the operation. But we're still then sending signals, in this case, directly from rather dumb sensors and into untreated into data storage for subsequent analysis. Now the next step here to improve back again to these sensors. We started placing sensors, more and more of them, as they became cheaper. So if we were interested in one point, the measurement point, we put a sensor there and a new sensor and a new sensor, and drowning in data. And also the sensors themselves became a problem because of the maintenance cost and the cost of installing. Now what we're doing with a digital twin is actually to make our analysis, our digital applications, our computers able to access something that they understand. They understand the digital twin, but they don't understand directly a physical object. So by using the digital twin to translate physical observations into a language or into the digital world, where the machines can access and rather freely, it opens up totally new possibilities, and it's then the last step before you have a fully digitized economy, because now all of the physical world in the end will be then interpretable by digital software programs.
Yeah, no, and just, I think you're bringing up two important points here. The first important point is this meta representation. So I think where you're going with this is, you can keep on adding more and more sensors, but maybe at one point a more efficient way of doing this is actually to simulate where other sensors could be, and that is the concept of having this digital twin. So you don't necessarily have to have a sensor. If we're just using a wind turbine, you don't have to have a sensor every millimeter. You could interpolate between the different sensors to understand what's going on. I think that's important. Yes. But I think the more important point that you're bringing up is what you were talking about in terms of machines can now understand the physical world, because this is key in my view, is is this digitization, putting it into a form, basically putting the physical into a digital form, because then you can interface it with the rest of the digital world, and that being the internet, and then that being, you can do a lot of interesting things with it in that digital form. So that, I think, is very key, because once it's in that digital form, you can do a lot of things with it, right? I mean, you could do, what are some examples then? Let's say now you have it in this digital form. What are some examples that you could do with an IoT product that you could not do if it didn't have a digital twin representation?
Well, we talked about the sensors that can be placed. We use virtual sensors that can then, instead of physical, that can be placed wherever you need them to be placed, which is not necessarily quite easy in the physical world. For instance, placing sensors in the middle of a material, impossible, but you can do it virtually. But these are these are quite clear advantages. You could do things, you could observe things here and now that you cannot do in reality. But more important is that there is a big difference between the physical object and its digital twin or its virtual manifestation. And that is that you can query the virtual representation of the history, but you couldn't do that from the physical object. The physical object kind of knows only what is happening right now. So a physical object, you cannot go out on a physical object and ask it, how is your fatigue situation? You cannot observe it really. But you can ask the virtual model how many fatigue generating cycles it has been exposed to. And you can ask it whether it has experienced over the last 24 hours a storm that has, or a situation that has been close to critical. So this is the ability to generate a history or to go backtrack in history is a clear advantage. And this is, as you would know, very important, or as you know, very important when you do big data analysis or you do use statistical methods or AI methods even to extract knowledge. This is one area. The other is the opposite direction, foresight. You cannot, in the physical world, play a future scenario into it. It just needs you. If you do that, you are actually here and now anyway. You would, of course, if you would try to simulate the future scenario in the physical model, the physical object, you could ruin it. But so we are able in the digital twin to play a future history and see how it would behave. And this is important, for instance, when you have a robot doing a task in a factory workshop. It lifts, there is a thing coming down the assembly line. It weighs 5 kilograms. So the robot lifts it in 5 kilograms, but and fast, it lifts it fast. But if the next object in line is 50 kilograms, what happens with the robot if it lifts the 50 kilogram object in the same speed as the 5 kilogram? Well, you would have a G-force 10 times the first one, which could foreseeably ruin some mechanism. So you would want then to simulate this situation by playing time, by playing future history, and make that feedback into the control system so that the control system could adapt and say, okay, well, I can't use my old strategy. I have to tune it up so that I won't ruin myself.
Okay, so you're using it to make modifications, let's say, to the controller, because you're doing a simulation and you're seeing perhaps it's out of bound, for example, a G-force, perhaps a machine can't take a G-force above whatever that is, whatever newtons that is, and then you would then say, okay, we need to slow things down or we need to do something different. Is that kind of what you're saying?
This is, it's a good description of what I'm saying. So if you're when we started this development, when we brought it up really to the attention of everybody, we had this case. Somebody said, "Okay, I'd read about this. Well, BMW or Mercedes came now fitted with an optical sensor that saw whether there were unevennesses in the road ahead, and would adjust behavior in the car accordingly." Now, this is a physical problem. If you know that there is a bump coming up, you could foreseeably, a priori or beforehand, adjust the suspension or the suspension system to make this bump the least of dangers. So this would be something you could do if you had a virtual or a digital twin of the car that kind of scanned ahead to find out how to feed back into the regulation system of the car.
Yeah, and this is interesting to me because in a way where I thought you were going with this was in predictive analytics, or in particular predictive maintenance. But really, this is it's a little different because, I mean, the time dimension is much shorter, but this is what would you call this? Because it's not really predictive analytics, is it? Or because I'm just trying to get my head around what this class of problem would be called or would be best described as.
Well, I would have liked to have that answer myself, the correct term, but our first usages of these digital twins or the virtual models or the real-time simulations would have been if not predictive, then in diagnostic situations. You diagnose the situation here and now in order to find out if you have to send an alarm, something has broken, and if it's broken, this is important. In the classical physics, everything is cause. This is cause and effect. There is not. It either is something or it's not. I mean, if you do this, then that will happen. It's a physical relationship. So to call it predictive, it's kind of it wouldn't be correct. It's more that it's a deduced situation. If you have some deflection here, you necessarily need to have that force responding to it, or force acting on it. So, but this is used in any case for finding if something has gone wrong or if you have to replace something, some degradation has taken place. And that's all used for monitoring.
But what in particular are you speaking about, though, here? What is being used for monitoring or deducing if something is going to go wrong or something has gone wrong? What is it that you're referring to?
I'll say that you have a bridge that's where you have something in the pillars has gone wrong. Some foundation has given way. This will be detectable in the physics. The physical behavior of the bridge will change. So you can then find out that something is not behaving logically. Something is not correct because the physics hasn't changed. The laws of physics haven't changed. So, and the model surely hasn't changed. So the reality must have changed. And when there is a mismatch between reality, as we observe it, and how it should behave, then we need to do something. So this is what I mean with diagnostics.
Okay. So you're comparing basically the model with what it should be and what it is, and then if there's some tolerance difference, then you're deducing that something is wrong, right?
Yes. So so it wouldn't be. It's predictive. It's predictive, but it's not predictive in the statistical sense. It's predictive in the cause cause and effect sense.
Yeah, and I think that's where I'm getting I think that's where I'm trying to bridge the two, because I'm very used to having this discussion with a statistical model as opposed to a Newtonian model. And when you're doing this statistically, then yeah, you can make predictions in a sense because they're based on some statistical accuracy. But here, your
Yes.
model is not a statistical model, right? It's going to be a physics-based model, and therefore it's doing things a little bit differently than I guess what I'm used to. Yeah, what I'm used to because what we're doing now is we're drawing in analytics, and analytics traditionally is working on statistical models. But in this case, you've got a Newtonian or a finite element model, or however you represent it, whatever representation. So you are doing sort of analytics. You are doing analytics, but it's a different type of analytics. Again, this is where I'm trying to get my head around.
Yes. We are doing analytics, but we're doing it with a head start, because, well, if you pick up your mobile phone now and you lift it up and you drop it, then you know that it will fall down. If you did that for the first time, trying to train use probabilistic methods or statistics to deduce now. It's because the law of gravitation. If you did this in a big data learning algorithm or in statistics, you would not be able to do anything much with it. You would then know that the first thing you would know is that the mobile phones are attracted to tables. Then you would do it several times, and you would increase this probability that the mobile phones are attracted to tables. But then you would drop the mobile phone to the floor, and some algorithm would then deduce that it's attracted down, it falls down, not to tables, but it falls down. But then you would gradually expand your experiences, and the algorithms or the probabilistic methods would gradually become better and better and better. So it's relying on several observations, big data, the law of large numbers. But of course, Newton found this out 300 odd years ago, and 300 years ago, close to, and so of course these relationships are coded into. I mean, they are law. You don't need to have algorithms recreate the laws. They are unchanged. But so that these by using a physical model with causal relationships, we can shift our focus into analyzing, well, why did the mobile cell phone fall, instead of, what was the cause behind it, instead of knowing the exact relationship between objects, between nature. So this is kind of the basic take that we have on this, that we are on, and of course also we now follow the individual, the instance, each individual. We don't follow a group of things, because in statistics we're on group level. We are thinking that if I have one thing that is grouped, that has the same category as other things, and these other things experience a certain behavior, then I assume that my thing that I have here experiences the same behavior. But of course, my thing may have a totally different history than other things in the same category. So that's why I want to know exactly what is the history or what is the behavior of my thing as opposed to the others, and thus maybe enhance the methods that we use. I'm not talking about replacing them. We're not talking about replacing anything. Statistical methods will have their relevance. Of course, artificial intelligence methods, pattern matching, neural networks, all this will obviously have their relevance, but so too will more physics-driven represent analytics have. So
and what we're talking about here, everyone, is, there's two ways to represent reality. Well, there's more than two ways, but we're talking about two different ways. One's going to be a physics-based, one's going to be a statistical-based. And the reason why you need the AI and the reason why you need all the statistics is because what you're trying to do is come up with a accurate representation. What we're talking about here, or what Arnulf is talking about, is, well, hey, for physics-based processes, and I think we need to separate this, right? Because this is going to work for a specific class of problem, and that's going to be a physics-based problem. For a physics-based problem, we kind of know how the physics works, and so we've got a head start. And that is, in one case, just using Newtonian physics, and we know how we have laws there, and we know how it works. Now, developing that model statistically, as you said, we need to go over many, many iterations to eventually figure out that things fall with gravity. How do you improve the model in this particular situation, or do you? I mean, what's the methodology for creating the model and then developing it over time?
Well, it's a good question, Bruce. But for starting with the model, most things, well, all man-made things are now, at least these of more complex composure will have a CAD model behind it. It will have some sort of digital representation before it's made.
Right, for mechanical objects. But I mean, again, if we go to the subatomic level and we start thinking about chemistry, and we start, there, then it's a different, or we go into the environment, or we go into economies, or, economics. But again, for mechanical, what we're talking about here is for mechanical objects, then
yes.
Okay.
Mm-hmm. Well, mechanical objects are all. The big difference is when you can make causal relationships. Where if A then B. If this is a rule, you don't need big data. You don't need statistical methods. You need statistics when you don't know the relationships beforehand.
You know it. Yeah.
And when there are and would want them when you don't know exactly what has caused a particular situation. So when you need to go beyond what you already know, then you would resort to AI methods.
That's one method. One method is to bring in AI to help you out. But okay, so that's how we improve it. Now, in your model, from what I've gathered so far, is you're using a base of finite element, although you come up with your own representation on top of that, or to replace the traditional or classical finite element. But now, is that model, once it's done, it's done? How is it created? And then is it ever improved?
Well, it would be created in the design of the thing, and then we would use the design model to create
in the CAD system, right?
Yeah, in the CAD system or in a process model. The processes are also, if you think about flow, flow is also, though not that easily represented, but it's more or less the same thing. Thermodynamics is also it's belonging to this physical realm.
Dynamics, thermodynamics,
absolutely, exactly those. Mm-hmm. We're not talking about quantum level. We're not talking about relativity, but we're talking about the classical physics. And then you would see digital twins of processes. You would see it of even chemical situations where if I mix two substances, then I know that the following will happen. These combine into a third, and this is modelable. So, and you could foresee that you would monitor some indicators, some important information about the physical situation, for instance, temperature, and see if the temperature goes above a certain level, then that reaction will happen if these two substances are together. And then you have a digital.
Okay, but take me back to the model. Take me back to the model, and I want to understand again. So we're saying we can create it with some system, and you're right. It could be a process for a certain subset of processes. It could be in a CAD system, and then is that it? Once it's created, is that model done? Is it improved over time, or is it does it have to be handmade to improve it? Or
No, I think you.
because this
Yes.
is critical in my view. It's critical in the sense, at least from a statistical methodology, is the dimension of time improves it. And this allows you to make predictions. This allows you to go back and forth in time like we were talking about. But I want to understand with a finite element, sort of finite element based model, what happens over time? Like, can we improve it? What happens there?
Okay, so if you have a system, if you have material, it's made of steel and steel corrodes. So maybe, let's say this is a situation. Then you would either have additional sensors to monitor or to observe the corrosion level so that you could automatically tune up the model. Because you're absolutely right, things change behavior, and it's not necessarily bad. It's just that they get worn down. But for every one of these information pieces, these changes, we would need observation. But we would only need enough observation so that we could detect whether this kind of degradation took place or not. For instance, then thickness of the wall of a particular vessel. Or we could combine, I think more likely we would then combine the digital twin that we're talking about, the direct calculation kind of, their direct simulation, with other tools, saying that now the behavior of this thing is changing, but based on statistics or based on deep learning, we find out that this is not caused by some anomaly, but it's only caused by natural wear and tear. So, then you would have a feedback into the digital twin so that it would adapt to itself. It would then represent its degrading or its aging history, and not, as you indicate, assume that when it's fresh and young, it will behave exactly as when it's mature and older.
Okay, so this is the interesting. So this feedback mechanism is very important in my view. And so what you're saying is the feedback is derived by sensing and then modifying the parameters of, let's say, I'm just visualizing it as a finite element model. So changing the parameters of the same basic finite element model, but just changing its parameters. Am I understanding that correctly?
I think you're understanding it very well.
Okay.
Yes, I agree. This is what would happen.
So you are going to have to layer, at one point, there is going to have to be, to modify those parameters, you are still going to need some statistical methodology, I would think, or maybe not. But I think this is important, is like we're talking about here, is the model will change over time. And so for it to be a digital twin, as the analog gets older, so does the digital have to get older, because otherwise you can't do the simulations on it accurately, right? And so this is this is a key. I think this is key when people are choosing their digital twin, to make sure that it represents whatever they're doing in a way accurately over time. Yeah?
Yes.
Does that make sense?
I think you're on to a very important point, because if we don't, this problem needs to be solved. The problem of updating the model according to and then be able to change to distinguish between what are behavioral changes that we need to act upon and changes that are simply natural. Yeah. So, as you say, also conclude the analytics needed to do this may come from the domain of realm of statistics or realm of artificial intelligence. But it may also then come from other types of sensors, particularly aimed for doing exactly this. But I think that we will see is that the digital twin is not instead of statistical methods. It's just that we use the digital twin to enhance the statistical methods, and vice versa. We use statistical methods to enhance the quality of digital twins.
Okay. No, that makes sense. So everyone at a high level, and Arnulf, you correct me here, but at a high level, what we're saying, okay, a digital twin is going to be a digital representation, whether we like the word twin or not, it's going to be a digital representation of the real world. The reason we're doing this is, one, we can then create simulations of the real world in ways that we couldn't necessarily do in the real world. And then two, we can interface it with the digital world. And once we interface it with the digital world, it allows us to do a whole bunch of things. And that takes us to the whole business side of this, which is it allows us to create value. So at a high level, is that a good high level, or what else would you add to that high level? Because people are listening to this, they're going, gosh, these guys just went down, pretty deep into the model and so forth. So why is it important to me? What would you say then? Is that accurate, or how would you put it?
Yeah, I think you're summarizing it right, and but I would just like to add that we've talked about the underlying physics of this and the technology, but of course what we are in the end doing is to replace or to enhance our old traditional methods of operating with digital. We, instead of going out and physically see something, we can detect it in the digital world. Yes. Instead of testing something in the physical, then we can test it in the virtual. And instead of going out and going back into records, we can now play back a certain history and monitor what we would do in the physical world through virtual sensors. So I think that we're doing the same things as before. We're doing it in the same high level as before, but we're using a particular technology to make it cheaper, simpler, faster, safer, whatever we can do. And I think I think that the cases, the usages we will put this to, we can't foresee it yet. We're just starting this development. We're starting this new era, and as long as we can solve the problems in the deep levels and expose them in a simple manner, then we will, on the high level, in the commercial domain, which we haven't talked about, in the business domain, see that we can do things totally different than we did. And that can just we can just use our imagination to find out what that is. Control systems, cyber physical systems, digital inspections, as talked about, smarter alarm systems. All of this.
Exactly. No, and what we're doing here is we're modeling the brain, not just the body, and that's where the value gets uncovered. So, Arnold, thank you very much. Where can people find out more about you and your company?
Well, our Fedem is now owned by SAP, and if you just go and look at SAP Leonardo, then you'll find that which is the SAP brand name for all cloud solutions, then we're under the IoT domain there. Fedem has its own website too, fedem.com, so you can, of course, look at us there.
Excellent.
We welcome all visitors.
Excellent. Well, thank you, and we'll talk soon.
Yeah, thank you, Bruce. Have a nice day.
Okay, that was an informative talk with Arnoff. This podcast goes vertical, deep diving into different topics each week. If you prefer a more horizontal and structured approach to learning IoT business and its orbiting technologies, check out my book IoT Inc., published by McGraw-Hill, or become a certified IoT professional by completing the ICIP training and certification program. For details, just go to www.iot-inc.com. Also go to www.iot-inc.com for an analysis of this episode, links to things that were mentioned during the episode, and very importantly, the episode's PDF transcript. Just search for the name of the episode or the guest. If you're new to this podcast, subscribe. That way you'll get every week's episode delivered straight to your device. Or, if you've been listening for a while, there are 3 ways you can support the show. You can leave a rating or a review on iTunes. Just go to iot-inc.com/iTunes. It only takes 1 click to leave a rating, a little bit longer to leave a review. You can share it on social. I'm on LinkedIn, to a lesser extent on Twitter. And of course, you can support this show by buying my book, IoT Inc., or the ICIP Training and Certification Program. It's how I pay the bills. Next week's episode is the digital twin and its relationship to the AEP IoT platform with Jason Shern and Jeff Miller of PTC. I hope you can join me then. I'm your host, Bruce Sinclair. Thank you for listening. Till next week, may your path to IoT business be a replicated one.
You have been listening to the IoT Inc. Business Show.